Let's take a look at the numerical estimation of limits. As an example, let's numerically estimate the limit as x goes to 0 of 1 minus cosine x divided by x. But before we actually get into the mechanics of how we do that, let's ask the question why. We have a perfectly good method for evaluating our limits, and that is to evaluate, in this case, since x is approaching 0, we use x equals 0 plus alpha. So we would plug in alpha, and we would have then at that point the expression 1 minus cosine of alpha over alpha. But now we see the problem. The problem is, what is cosine of alpha? Let me separate that there. And we will have an answer to that question of what is cosine alpha later. But you may still at times run into functions for which you don't know how to evaluate them at an infinitesimal. So what might you do? One thing you might try is the graphical approach. On the graphical approach, we simply graph the function. We look at what the graph looks like, and in this case it would actually look something like this. And you would see that the limit appears to be 0. But the problem in looking at a graph is you might say that looks like 0, but depending on your scale, you might be off. Perhaps it's 0.003 or some other similar value. So it's hard to tell very precisely what a value is from a graph. So then maybe we would want to verify that numerically. So what would the idea be? Well, if we can't get infinitely close like we can with an infinitesimal, then maybe we'll try getting just somewhat close and seeing what the value of our y-coordinate is. And then we can get closer and see what that y-coordinate is, get closer and see what that y-coordinate is. And as we look at movement of our x's toward our target of 0, then we would see movement in our y-coordinates possibly toward a particular value that would be our limit. So let's try that. So from the right, if I allow my value of x to be 0.1 and then 0.01 and then 0.001, then those values would be getting closer to 0. So that's one way to let x approach 0. Now notice here I'm getting closer by an order of magnitude every time because we need to get much closer and closer and closer to 0, so closer to our target. That difference we want to make very, very small. And if you just go like 0.8, 0.6, 0.4, 0.2, then all of a sudden now you're at 0 in that next step, and it's hard to tell exactly what your progression might be doing. And so it really does help to go by an order of magnitude closer to your target each time. So we simply then evaluate 1 minus cosine x over x. You can do this on a calculator or on a computer. You would have, say, 0.049958 for the value of that expression when x is 0.1. Remember, we're evaluating it in radians. When x is 0.01, you would have 0.004999, but that means it would round to 6 decimal places to 0.005000. And then when you let x be 0.001, you'd have 0.000500. So that certainly looks like that's also going towards 0. And from the left, we would pick negative values as we're going toward 0. And at that point, you would have negative 0.049958, negative 0.005000, negative 0.000500, etc. It still looks as if it's going to 0. And at that point, we would conclude that the limit as x goes to 0 of 1 minus cosine x over x is 0. Now, a couple of technical details here. the only reason we use negative values of x when approaching from the left is because we were approaching 0. If you're trying to approach 2, then from the right you'd go like 2.1, 2.01, 2.001, but from the left you would go 1.9, 1.99, 1.999, etc. if x was approaching 2. So the idea again is you're just approaching your number from both the right and from the left, and approach 0 from the right and from the left you've got positives and negatives. Okay, and then we just look to see what our y coordinates are going to. Here they're going toward 0, but they could have gone toward 27 just as easily. So whatever number they seem to be approaching, that's what you get. Now, a couple of comments are in order at this point. The idea is, again, if we compare this to our earlier work, with infinitesimals, we know that we are infinitely close. And in fact, if we have the same value for every infinitesimal, that's our exact limit. So we can get the exact limit from there. But when we are looking at numerical estimation, we're infinitely further away. We're close, but we're not infinitely close. And what that does, it means then we have to watch the movement of our numbers and just hope our guess is correct. And in fact, it turns out that sometimes our guess will not be correct, or sometimes you try this and something weird happens. So this is a method that's imperfect. So how imperfect is this method? Let me give you an example showing the need for caution, or demonstrating the need for caution. Let's try to numerically estimate the limit as x goes to 0 from the right of the square root of x squared plus 16, subtract 4, divide by x squared. So, I will use a TI 83 calculator and use values of x, and then I'll call our expression f of x. If I allow x to be 0.1, you can verify this on your calculator. You get 0.1249805. If you allow x to be 0.01, the calculator says 0.1249998. If you allow x to be 0.001, you get 0.1250000, and it sure looks as though we're approaching 1/8. So, if you conclude that your answer to that limit is 1/8, you would be correct. But let's try continuing. Suppose that you weren't content just to stop that close, and we wanted to look at other values of x, like 0.0001, 0.00001, and finally 0.000001. Your value of your calculator would say 0.125 and then 0.125, and you would be happy again. It looks as though it's 1/8, but at 0.00001 it'll spit out the answer 0. And that's actually the wrong answer. And if you think, well, that's just the calculator's problem. No, if you try your favorite computer algebra system, you'll find that the same phenomenon occurs. Now, why is that? The answer is that the calculator or your computer algebra system are trying first to calculate square root of x squared plus 16 for values of x that are given here, which is 4 point whatever. And if you get too many zeros past there, then whatever the answer might be out there, it would say, cut that off and say it's just so close to 4 it can't tell the difference. Then when it takes that minus 4 and divide by your x squared, it's going to say it's 0 because your two values in the numerator were so close together compared to the amount of precision you've got that it just can't handle the difference between them. Now there's actually an entire subject in mathematics called numerical analysis that tries to help deal with such phenomenon, how you can do calculations such as these without having problems such as the one that I've created here. But this does show that there are limits to using technology into numerical calculations that we would always run into. And that's why mathematics requires then an approach such as the use of infinitesimals or the classical methods for evaluating limits in order that we can find those limits exactly without having to rely on imperfect calculations. And one final comment here, there is a screencast that shows what the graph of this function looks like too, to show that there are continued problems with looking at the graphical methods as well. So again, we do have the need for exact methods, and that's what our infinitesimals are all about.